After chapter 12, chemical kinetics, equilibrium is going to be a cakewalk. But the reason we took chapter 12, in fact, the reason the authors put chapter 12 before 13 is that equilibrium is understood better in terms of reaction rates. Now, historically speaking, chemical equilibrium was investigated earlier than kinetics because the technologies and the understanding at that time was better for studying equilibrium than it was for kinetics. But now we find that equilibrium is understood better if we have a grasp of kinetics. And like I said, the kinetics required an advancement in a topic called thermodynamics. And once that was accomplished, then kinetics took off, and it actually surpassed equilibrium in importance. But by definition, equilibrium is, let's make up just a generic equation. Let's see, there's your coefficients. And there's your coefficients. So when we look at the reaction, see the reaction in the macroscopic, in other words, what we can see, what we can observe and measure, what we see is that eventually, even if you start off with only reactants, then you'll end up with some products, but you'll still have some reactants, usually. Now, there are cases where the reaction goes so far to the right that there's not much left here, but there's always a little bit left. It's just difficult to measure. And that's what we see. We see that the reaction apparently is not changing, at least in concentrations. But on the molecular level, what we're seeing is that the rates, the forward and the reverse reactions are still occurring, while we think that there's nothing happening. So the forward one, of course, will have a constant of K for the rate law. And then the reverse reaction will have its own K for the reverse. I shouldn't write it that way, because that implies that this is the inverse of that, but it's not. So on the microscopic level, what you're seeing is a balance in reaction rates. The rate of the forward reaction equals the rate of the reverse reaction. That's why we don't see any change in the macroscopic world. Appears to be static, but it's not. It's very dynamic. Now, if we measure concentrations, of course, for this equation, yeah, that's good. Let's use this one. Oh, this is the Haber process. If we start off with only reactants, and that's what the graph is showing, the blue line is the hydrogen, and the green line is the hydrogen, the blue line is the nitrogen. And at the very beginning, there's no ammonia. We see the concentration in that graph, it's at 0. But as the reaction proceeds, we lose some of this, we lose some of that. In fact, 3 times as much of this we lose as that. And we end up with twice as much as this in concentration. So eventually, the point at which we reach equilibrium, we're measuring concentrations to be unchanging. Let's see. All right. So if we look at it in terms of reaction rates, what we're going to see is the forward rate. And when we studied kinetics, we studied them at the very beginning, right? Initial rates. So we see at that 0 point, the reaction rate is at its highest. It's producing products at a given rate, and we're so close to the beginning that we don't see any return reaction. That's why we study reaction rates very often in terms of initial rates, because then we don't have any competing reverse reaction to muddy the waters. But eventually, if we let the reaction continue, we find that the forward rate and the reverse rate match. They're exactly equal. All right. So with this equation, we're going to introduce, it's kind of a teaser. We're going to introduce a topic that we're going to cover in more detail toward the end of the chapter. But if you see, you've got water as a gas combined with carbon monoxide, gives you hydrogen and carbon dioxide. Then if the reaction rates are exactly the same, they're balanced, we're at equilibrium. What would happen if we added more water to the flask? Right? Now the concentration of water is not the same as it was at equilibrium. And what you're going to find is that with that increased amount, right, we look at the reaction rates. So if we increase the concentration of a reactant, the rate's going to increase, correct? We learned that in chapter 12. Well, if the rate increases in the forward direction, what happens in the reverse direction? Well, initially, at an instant of time, the reverse rate doesn't change. But as you start to produce with an increase of reaction of water to hydrogen and carbon dioxide, you start producing more products. Now they become reactants in the reverse reaction, and the reverse reaction increases its rate. And you will eventually reach a point where the reaction rates will balance again. All right. What happens if we add more hydrogen? Instead of water, we're at equilibrium, we add more hydrogen. Well, the same thing happens in reverse. Initially, you've got an increased concentration of hydrogen, which increases the rate in the reverse direction. And only when you start to produce water and carbon monoxide, do you get an increase in the forward reaction, and they will eventually balance. All right, so we can express the equilibrium of a chemical reaction in mathematical terms. It's called the law of mass action. And it was developed by two Norwegian chemists, Peter Wegg and his brother-in-law, Goldberg. They were studying solutions, right? They wanted a way to express mathematically some way to define how reactions proceed. And there was some interest in those days in the chemical dynamics, they called it. We call it kinetics now. And how they relate to chemical statics, which we call equilibrium. So they discovered that what they could do was express the concentrations of the reactants and products in terms of familiar units of measure. And the familiar units of measure in those days were molarity, right? Because they were working with solutions. So the molarity of C and D were determined, and the molarity of A and B were determined at equilibrium. And when they did that, they noticed that this expression is a constant. Molar concentration of C raised to its coefficient times the molar concentration of D raised to its coefficient in the numerator. Then in the denominator, we put the reactants. And that, for a given temperature, must remain constant. For a given temperature, that expression is a constant. So unlike in kinetics, we learned that you can't use the coefficients of the overall reaction to determine the rate law. But the law of mass action is easily written with using the coefficients as powers. Now, K, what you're going to find is if you look K up for a given reaction in a reference manual, you won't find any units. We leave the units of measure out simply because the sky's the limit, right? With these powers in here, right? Remember, anything you do to a number, you do to the unit. So with these powers in here, we raise the units to these powers and we get an infinite possibility for different reactions of units of measure. So what we do is we just leave the units off. What you will find in the reference manual is an expression of what was the original concentration. Was it in molarity? Was it in partial pressure? If every reactant and every product is a gas, then sometimes we express the concentrations in terms of partial pressure of A raised to the A Late power. Right? That's a possibility. So in the reference manual, we just tell you what were the original concentrations. And then you have to be very careful with your calculations in order to come out with the right answer. All right. What we're going to use, remember Hess's law? Think way back last semester. Hess's law, where we combined equations to determine the enthalpy of the overall equation. Okay. So we can do the same thing with these expressions. If we have more than one equation that we want to add together to give us this one, then what we need to know is how can we manipulate this expression and give us the correct rate constant for each of the additive steps, and then put them together to give us the overall K for that reaction. Well, we need to understand what happens when you do certain things to any one of the equations. If we have a K for an equation, so this is just one step in we're going to add this to something else. If we need to multiply this by a value, right? Right, this is balanced, but we need 2 of these or 3 of those. Then we multiply it by a value here. When we do that, what does that do to this expression? Well, now the expression with that A multiplier is N times A. Right, let's do it this way. N. Right. So now what does that do to our expression? Well, now it's C to the NC and D to the ND and A to the NA and B to the NB. So one of the mathematical manipulations you can do is you can factor out powers. Each one of these is multiplied, each one of these powers is multiplied by n. So what we can do is we can say, we can factor out those powers. Now it becomes like that. Okay, we just took this n out, factored it all the way out. If we were to expand this again, we just say n times that, n times this, n times that. So what does that mean? Well, this value right here is the original k. Right? So this k, if we multiply this times some whole number, or even a fraction for that matter, then what we get is k to the n power is equal to this manipulated k. Okay. The other thing we can do is suppose we need the reaction in reverse. Let's remove these now, talk about it as if it were the original. If we needed the reverse reaction, how would that affect this expression? Well, the reverse reaction, we could say K like that, would simply be, now these are the products. So they would go in the numerator. And the products here are now the reactants, and they would go in the denominator. Okay, so what does that mean? That means our new K is actually equal to the original K inverted. I'd say 1 divided by the value. If we invert the equation, we invert the expression. Right. Now, let's see. Let me go back to our original discussion here. Get rid of these. There's a difference between the equilibrium constant and the equilibrium position of a reaction. The equilibrium constant is just that. It is a constant. As long as the temperature doesn't change, then this is a constant. No matter what the concentrations you put in here, eventually when it reaches equilibrium and you determine the concentrations at equilibrium, put them in the expression, it's always the same number. But if we start off with different values here, even if we start off with something here, here, and here, when it reaches equilibrium, it may be at a different position. The concentrations will not be the same as if you started off with only reactants and produced products. So the equilibrium position has an infinite number of possible concentrations of reactants and products, while the equilibrium constant is just that. It is constant for a given temperature. Now, when we write the K, there may be subscripts. Sometimes you'll see it like this, just KEQ. That generally means that the concentrations are in molarity. If we write it with, let's see, this, K with a subscript P, then the concentrations are in partial pressure. Right? If we write it like this, that's a special constant that is reserved for water. If we write the equation for water, we find that water is in equilibrium with protons and hydroxyls in aqueous solution. And this is a pure liquid. So if we write the expression for this, okay, I'm kind of jumping ahead here. We write the expression, this is going to be in the numerator. Right, it's to the first power. This will be in the numerator to the first power. And we would expect to put water in the denominator. Except, and I think this is on the next slide, pure liquids don't change concentration. We only want factors in there that will change their concentrations to reach equilibrium. So that's why this expression excludes that one. So this concentration of hydrogen ions, concentration of hydroxyl ions gives us a Kw that's exclusive for water. And we'll get into more of this in chapter 14 and 15 when we talk about acid-base reactions. You may also see this one, and we'll get into this one later also. This is solubility product. And if we write it, say we have a salt. Let's see, let me mix, how about this one? Silver chloride. Right? We learned some time ago that silver chloride, when silver ions and chloride ions get together, they form an insoluble compound, they precipitate out. But the fact of the matter is, there is some dissolution, not much, a little bit, can be quantified. Right, so this can go into aqueous solution, and this would be an aqueous solution. And here again, that solid concentration does not change. Right, solids and pure liquids don't change concentration, so it stays out of the expression. That means the solubility product for this expression would simply be silver and chloride. That's why we call it the solubility product. It's only a product of these two ions and their first power because of the equation. But that's what KSP stands for. And then this one we're also going to do later is the formation constant. Oops. Constant. This is usually associated with the formation of complex ions. Right, so we'll talk more about that later. Excuse me. In fact, we're going to do a lab on this one. All right, so those are special cases for the K subscripts. And here's our example with Haber-Bosch. And since all reactants and products in this equation are gases, they can be expressed in terms of partial pressures. And that's the expression we have on the left. Partial pressure of ammonia, of course, is a product. So it goes in the numerator and to the second power. And then nitrogen and hydrogen go in the denominator. We can write it both ways. We can write it either as partial pressure or as molarity. But the K's will not be the same. Why? Because they're different units. But they can't be the same. If they're ever the same, it's purely coincidental. But they are related. And I'm going to give you that equation in a minute. But we can calculate at equilibrium, say we have this for an example. If we have this many atmospheres for each one, then we can calculate the solubility, the equilibrium constant in these terms, and it becomes 3.9 times 10 to the fourth. All right. If we know Kp in this case, and we want to determine the KEQ, what we need is this equation. Right there. So this would be in terms of molarity. This would be in terms of atmospheres. And we know this is atmospheres because the R that we use is this one, 0.08206 liter atmospheres per mole K. Right, so we know that the pressure has to be in atmospheres. And we know that the temperature's in K, and we know that the concentration is molarity because liters over moles cancels moles over liters, which is molarity. All right, so temperature has to be in Kelvin, obviously, but what do we mean by this figure right there? Well, if we look at that equation again, right, we have nitrogen plus hydrogen yields ammonia. And those are all gases, of course. The change in molarity is it went from this one to that one. So how did it change? Well, it started off with 4 moles, right? 3 plus 1, 4 moles of gas. Ended up with only 2 moles. And unless you're told otherwise, a delta means final minus initial. So we ended up at final 2 minus initial 4. So the change is minus 2. So for that equation, delta N equals minus 2. And N in this case is my abbreviation, well, typically abbreviation for moles. So I think we're going to use this as an example. Yeah. So if we know that Kp here is 3.9 times 10 to the 4th, we want to know what K is. So we know what R is, 0.08206. I'm going to leave the units out for convenience. And this is times temperature, which they gave us as 35 degrees. So 35 plus 273 is 308. And this is raised to the minus 2 power. All right, so now all you have to do is solve for K. Right? And K turns out to be 2.5 times 10 to the 7th. Now it's a different value because we use different units, molarity. But it's still the same reaction. Right? The reaction hadn't changed. We changed the units, so the value changes. All right. Now let's say a little bit about comparing the phases of reactants and products. If all the reactants and products are in the same phase, and here's our example, right? The Haber process, they're all gases. That is a homogeneous equilibrium. If we have everything in aqueous solution, right? Hydrocyanic acid yields hydrogen ions plus cyanide ions in aqueous solution. That's a homogeneous, that establishes a homogeneous equilibrium. And you probably guessed there is heterogeneous equilibrium. For a heterogeneous equilibrium, you have 2 or more different phases. So conceivably, we could have gas, we could have a solution, we could have a solid, we could have liquid, all 4 of them in there. I can't think of one off the top of my head, but it's possible. In the first case, we have potassium chlorate, a solid that decomposes into potassium chloride plus oxygen. Right? We used to do this in the lab as a joke. We dissolve potassium chlorate in water, fairly concentrated, and then we dribbled it on the floor, and it would dry to solid potassium chlorate. And all you needed was a little bit of physical shock, and it would decompose into potassium chloride and oxygen gas. And oxygen gas, of course, expands. It makes a pop. So when some unsuspecting student or instructor, for that matter, walks into the room and steps on one of those little spots, and they're hard to see, you get a pop underneath your foot. Perfectly harmless, right? But you need a little bit of energy to get it going, right? For this reaction, let's go ahead and put this one up here. Potassium chlorate solid is in equilibrium with KCl solid, and this is 2 plus oxygen gas. Yep. The equilibrium expression for this one is going to be just that. Because that's a solid and that's a solid. This is the only one that will change its concentration. Now, I will add that this reaction obeys stoichiometry rules, right? Once you run out of that reactant, it stops. Doesn't matter what happens over here. If you ever run out of this reactant, and it would be difficult to do if it's in equilibrium, of course, it's always going to produce some of this, but hypothetically, if you run out of a reactant, the reaction stops. And then here's the decomposition of water into hydrogen gas and oxygen gas. Water is a pure liquid, which means it does not enter into the K equation. So for that equation, you would simply have hydrogen gas to the second power and oxygen to the first power. That would be the expression for that equilibrium. And this is the slide that I've been using all along. Oh, excuse me. That should be 3. Yeah, 3. There you go. So pure solids and liquids present in a reaction equation do not enter into the equilibrium expression. So what type of information can we glean from the K value? Well, if we have a situation where A plus B is in equilibrium with C plus D, and we write the expression like C and D and A and B, then what does that tell you about the reaction if you know that K is, let's say K is much greater than 1. Right? If it's very large, that means you've got a lot of this and very little of that, right? Mathematically speaking. And that translates into a lot of product and not very much reactant. If we went the other direction, right? Say K is much less than 1, then the situation is reversed. You have very little product and mostly reactant still in the situation. So that means the reaction tends to be mostly to the left, as written. All right. So if the equilibrium lies to the right, the value K is large, greater than 1. Now your authors may say, simply it's just greater than 1, right? So it could be 1.001, and they're saying it's one direction. Well, the problem with that is, how do we calculate K? We calculate K with these coefficient powers, right? So that can muddy the waters. If you get the right powers, your K could be less than 1, but it's actually to the right. Right, so that's why I say very large values greater than 1, then you're fairly safe in saying that the reaction lies to the right. And very much smaller than 1 lies to the left. All right. Now, before we can do some calculations and actually determine from initial conditions where is going to be the equilibrium position for our reaction, we can calculate concentrations. And I'm going to show you the method in a minute. But first, we have to say, which way is it going to move? Right? If we have reactants and products given to us, brought together in this reaction, then how do we know which direction it's going to move? We need to know that in order to do the calculations. Well, one way, the easy way is if you're only given reactants and no products, you know which way it's going to move, that way. Or if you're given products, it's going to go this way. Or if you're given reactants and one of these is 0, it's got to go that way. But if you're given real values for each one of these as starting positions, how do you know? That's where the calculation of Q comes in. Q is modeled on the K expression. So you would take the actual concentrations, and I'm going to use parentheses instead of square brackets here. Right? Calculate your Q, and you get some value. Then how do you know which direction it's going to go, the reaction is going to move based upon the Q? Well, we compare the Q to the K. Right? The easiest one is if the Q is equal to the K, right? That means we're at equilibrium. I mean, that's very difficult to do. If you're going to put concentration, concentration, here, all 4 of them together, it's difficult to meet exactly Q equals K, right? Because of experimental error. But there's always error in measurement. But what if the Q is greater than K? What does that say? If this Q is greater than that K, that means you have more product than you should have and less reactant. So if you have more product than you need, it's going to move to the left, correct? So we're going to shift to the left for the reaction as written. And the reason I say that is if you write it in reverse, it's going to be the other way around. Right? So when you say left, right, for an equilibrium shift, you have to reference a balanced equation. If you don't reference a balanced equation, then left and right means nothing. All right, the other possibility is Q is less than K. If Q is less than K, that means we don't have enough numerator and too much denominator. We have too much of this and not enough of that, reaction is going to move to the right. Now, if you can reason it out like that, that's fine. But if you're stuck, I mean, if you can't wrap your mind around this comparison, then just memorize it. If Q is greater than K, it moves to the left. All right. Well, let's take some examples. See how we do with time. 9:15. Okay, we're not even in the lab yet. All right, for this equation, we have iron 3 plus as a reactant, and we also have thiocyanate ion as a reactant in equilibrium with this species here. I think we're going to use this one next in our lab. This is a complex ion. And you know you've got it when you put these two together. This turns a bright brick red. Okay, suppose we are given an initial concentration of 6 molar in this one. Let's see, we got, there we go. 6 molar in iron and 10 molar in thiocyanate. Right? That's our starting position. So if this is our starting position, how much of this one do we have? 0. Right? That's the beginning. This is known as the initial starting position. What kind of change are we going to get? Well, we have to figure that one out, because we're given an equilibrium value for the iron 3 thiocyanate ion at 4 molar. We're given this one. This is at equilibrium. What I've just built is called an ICE table, like for obvious reasons. Initial, change, equilibrium. So from this information, we can deduce these other two concentrations. And we need those in order to answer the question, which is, what's the equilibrium constant? So with this balanced equation, we have 1 to 1 to 1 ratio. Then if we end up with 4 molar here, how did it get there? Well, the change was a plus 4 molar change. That's the only way you can get there. Where did that come from? Well, if it's 1 to 1 to 1, we had to lose 4 molar on this side. And we had to lose 4 molar here. Right? It's the only way it can happen. 1 to 1 to 1. So for every one of these, you get one of those. For every one of these, you get one of those. So now we can calculate the equilibrium concentration of thiocyanate at 6 molar, and for iron 3 plus at 2 molar. Okay, now we can calculate the K. K is going to be 4 molar in the numerator and 2 times 6 molar in the denominator. So what is that? 4 divided by 12 is the same as 1 divided by 3, isn't it? So that would be 0.333 would be the constant for this reaction as given. Right. There's the ICE table and the calculation. 0.333. Now that we know this K value, we can take this equation and change the concentrations and determine a different equilibrium position. Right? Because this isn't going to change, but these values might change. But when we put those values in this expression, we always get that value. I think that's what's coming up. Okay, now that we know our K value at 0.333, right, let's put it over here. K equals 0.333. Now we're going to change the values. 10 molar here. Let's see. Yeah, we'll chop off one of the zeros. 10 molar there. And 8 molar. So we're starting from a different position there. Now, same temperature and none of this. So we know the reaction is going to the right. Okay, so how do we get down to here? We have to use a little algebra, right? Create an unknown. If we're going to move from this position to an equilibrium position, we know that it's moving this direction. So it's going to add some over here, some amount. It's going to subtract the same amount from this side. All right. So that means we got an X here. We got an 8 minus X here, and we got a 10 minus X there. So if we set up our equation, is equal to that X in the numerator, and in the denominator we have 10 minus X and 8 minus X. Now we solve for X. Let's see, we got it set up on the next slide, maybe. Yeah. Okay. There's a trick that sometimes we can use. If this value is extremely small, which it isn't, all right? But if it were very small, we know that the reaction would not go very far to the right. That means X would be extremely small. And if X is very small, then we can say, all right, it's a lot smaller than 10, a lot smaller than 8. We can just throw it out, these two, make 10 and 8 there, and then solve for the other X. Okay, but we can't do that here because this value is too big. All right, so we have to solve for X, and that's what the, rather than not going through the whole rigmarole up here. Notice that what you got is you expand the binomial. Remember that from math? Expand this binomial, you get a quadratic equation. Right? X times minus X is X squared. Right? And then 8 times minus X is minus 8, and minus X times 10 is minus, so that's minus 18X. And then 8 times 10 is 80. That's your quadratic down here. That would come over here, multiplied times 0.333. And that would be equal to X. So what you have to do is propagate this 0.333 through the whole thing and then put X on one side. Oh, excuse me. No, you wouldn't. Not if we're going to solve a quadratic. My mistake. You get this X over here. After you've done that, then this becomes a minus X on this side, and that's 0. Remember, you can't solve a quadratic unless everything, the quadratic is equal to 0. Then you can use your equation, which I keep on the back of my calculator. Yes, I never could remember it anyway. So it's going to be, once we get it in the quadratic form, then X equals minus B plus or minus square root B squared minus 4AC all over 2A. Well, what are those values equal to? Well, the A, of course, is the coefficient of X. The B is the coefficient of X squared. B is the coefficient of X, and C is the constant number. And you end up with 2 values, right? Because you got a plus minus. And the 2 values are X is either equal to 15.99 or 5.0. Then you have to decide which one makes sense in the real world. Well, if X is 15.99, where did it come from? It can't come from these because that's only 10 and that's only 8. So if it's 1 to 1, 15.99 can't happen. It's impossible. So your only choice is 5. X would be equal to 5. If X is equal to 5, let's see. Yeah, that answers the question. Right? What's the concentration of the complex ion? Yes. And that also introduces a trick that you should try to use whenever you're going to solve one of these ICE tables. Try to pick the unknown that will answer the question, if at all possible. In this case, we picked X. So X would answer the question. Once we find X, we have the answer. Sometimes it's not possible. Sometimes you have to pick an unknown that's that requires that you do a calculation to get the answer. All right, so if we've done this, if the question were, what's the thiocyanate ion concentration at the end? Now we have to take X, subtract X from 8 is 3. Right? So 3 would be that one, and 5 would be this one at equilibrium. You have to do another calculation to get your answer. But since the question was, what's that one? Then we got our answer. All right. So the position could change. All we need is to know what the initial concentrations are, and we get a different equilibrium position. If it's 6 and 6, we have 6 here, 0 there. Similar situation here. We have 6 minus x. We have 6 minus x here. Put it in our equation, and we get a quadratic again. And if we do the calculations, we end up with x is actually 3, which makes sense, right? Because these values are smaller, and we're going to end up with a smaller value over here. Instead of 5, we end up with 3. Okay, these are just steps that you should follow to solve an equilibrium problem. First, you have to, actually, I left out one step. You got to write the compounds and the ions exactly right. If you're given the names, then you got to be able to write the formulas. Then balance the equation. Then write the equilibrium expression for the law of mass action. Then list your initial concentrations and start your ice table. Then if you don't have one of them as 0, if one of them is 0, you know which direction it's going to move. But if you have values for each one of the reactants products, then you calculate the Q and say, which way is it going to move? Then you pick your X, preferably so that when you solve for X, you have the answer. Then you substitute these expressions in the equation and solve for X. Here are possibilities. Right, these. We could do all of them. Let's see, one of these is actually, let's calculate the Q's for each one of these first. See which way they're going to move. All right. So the first one is 9, 5, and 1. So the Q for the first one is going to be 1 divided by 9 times 5, or 1 over 45. That's much, much less than 0.3, right? So if it's much less than 0.3, we don't have enough product. That one's going to move to the right. Right? How about the second one? 3, 2, and 5. 3, 2, 5. So the Q for this one would be 5 divided by 3 times 2, which would be 5/6, right? That's a lot bigger than 0.33. So this one's going to move to the left. It's got too much product. And the last one is 2, 9, and 6. 2, 9, and 6. So this one is going to be 6 divided by 2 times 9, which is 6 divided by 18. 6 and 18 is 3, isn't it? This one is exactly 0.333. This one is equal to K. That one's not going to move at all. All right. So we just run through that same calculation for each one of them. And these are the let's see, 2, 9, 6. Okay, these are the starting positions. Six, 2, and 4. Is that right? No. Those are not the starting. Those are the equilibrium positions. Right. The last one is unchanged because it's already at equilibrium. So you just have to run through that same calculation set in order to answer the questions. And you've got plenty of practice ahead of you with the review document. So I'm not going to beat that horse right now. Let's see. All right, so here's Here's our Haber-Bosch process. We have to balance the equation and then calculate the K. Let's go ahead and put it up here. So I spread them out like this so that we've got plenty of room. Okay. So a 2 mole sample of ammonia is introduced into a 1 liter container. 2 moles in 1 liter is 2 molar, right? Introduced into a container at a certain temperature. The ammonia partially dissociates according to this equation. Right? So we're starting off with none of that. Oh, I'm backwards. Excuse me. Let's try that again. So this one would be ammonia. And this one, let's scooch it over a little bit. This one would give us nitrogen gas plus hydrogen gas, like that. Now that's balanced. And we're starting off with 2 molar. All right, so we're starting off with initial concentrations of nitrogen and hydrogen at 0. At equilibrium, 1 mole of ammonia remains. So at equilibrium, we got the same size vessel, but now it's only 1 mole. So that's 1 molar concentration, correct? All right, calculate the value of K. All right, so what's going to happen? It's going to move that way. And how much did it lose? Well, it lost 1 molar. And so if it lost 1 molar, the ratio is 2 to 1. So how much nitrogen did it produce? Half of that much, right? If the ratio is 2 to 1, we actually added 0.5 molar. And if the ratio is 3 to 1 here, we added, let's move back over. We added 1.5 molar of hydrogen. Okay, so now we have our values. And we can calculate our K. So the K is going to be nitrogen, hydrogen to the 3rd power divided by ammonia to the 2nd power. Now we put in our values. Nitrogen is 0.5 molar. Hydrogen is 1.5 molar cubed. And ammonia is 1 squared. Okay. So what's 1.5 cubed? I have to put that on my calculator. Let's see. There's my key. So this one is going to be 3.375 times 0.5 divided by 1. Okay, so 0.5 times that one and divided by 1 is 1.69 is our K for that reaction. So what does that mean? Well, it's probably favoring the right-hand side. Right. There you go. Now that we know the K, we can change these concentrations, just put anything in there we want and find out where we're going to end up. What position. All right, we got a different one coming up, looks like. Based upon this equation, N2O4 gas is in equilibrium with 2 NO2s. Right? And we're given the K. K equals 4 times 10 to the fourth. Minus 4, minus 4. There we go. Okay, initial concentration. 1 mole sample is placed in a 10-liter vessel. So the initial concentration of this guy right here is 1 mole in 10 liters is 1/10 of a molar, isn't it? Let's see, 3 significant. And we got nothing there. Right, so what's the change that we should expect? Well, we're going to lose something from this side, but the question is, what's the equilibrium concentration of each one? Well, if we're going to calculate both of them, then we can pick the X wherever we want it to. We're going to lose some of this one. So that's 0.1 minus X. And we're going to end up with 2 times that much on this side. Right? Okay, now we can put it in our expression. 4.00 times 10 to the minus 4 equals 2x squared and 0.1 minus x. All right. This is one of those cases where the X is going to be really small because the K is so small, it's not going to move very far this way. So that X is going to be really, really small. The question is, which one do we want to negate? Right? If we say this one is 0, then that gives us 0 divided by a number which is infinity. Right? So we can't do the numerator. We have to do the denominator. So we say it's approximately 4x squared, right? I just squared this one, divided by 0.100 and leave the x out. Okay, so 0.1 on this side of the equation times this value makes that one a minus 5. And that's 4x squared. X squared, oops, then is equal to 4 divided into this one, which is 1 times 10 to the minus 5, and x equals the square root of that value. Which is 3.16 times 10 to the minus 3. Okay, that's x. Right, so if we calculate the concentrations of these values, then 0.1 minus that value, 1, is 9.68 times 10 to the minus 2 molar, and 2 times that value is 6.32 times 10 to the minus 3 molar. Okay, let's see if the slide agrees with me. At 0.097. They rounded it off to 2. So we'll move it 2 places to 0.097, that's correct. And then 6.32 times 10 minus 3. Okay, what we did was we said X is insignificant. It's so much smaller than 0.1. Is it? Well, yeah, like half of that is 1.6 times 10 minus 3. It's much smaller than, by 2 orders of magnitude smaller than 0.1. But the question also is that small enough? And in order to determine small enough, we use the 5% rule. The 5% rule says that if we take these values, these equilibrium values, and plug them into the equation, is it going to be within 5% of the true K? So if we calculate K based upon these values, oops, then we would put this one in the numerator and it's going to be squared. And then this one in the denominator, right? And calculate what our K is based upon the answers we got. All right, so I got that one, I'm going to square it. And then 9.68 minus divided into that. And I get 4.13 times 10 to the minus 4 as our calculated K. Well, our given K is 4 times 10 to the minus 4. Right? So is that one 5% of this one, or is it less than 5%? What's the difference? Right? 4.13 minus 4 divided by 4 times 100. That's the relationship of this one to the true K. All right, so 0.13 and divide by 4. And the reason I can do that is because they're all the same power. They're all the same power, so those cancel out anyway. So I get, let's see, 100 times that. Yep. So I get 3.25%. So we're less than 5%. We're justified in making that approximation. All right. Now, Le Chatelier's principle. That's what I was hinting at in about the third or fourth slides. And this is the one we're going to do next week in the lab. We're going to use Le Chatelier's principle. Le Chatelier was a Frenchie in the 19th century. And he noticed that when a system was at equilibrium, if you did anything to disturb it, right, if you stressed the system in any way, any valid way, then the system would respond to reestablish equilibrium. So what we did in those first two, earlier slides was we added a reactant and shifted to the right to reestablish equilibrium. And then the following slide, we added a product and it shifted back to the left. So we're going to look at this equilibrium problem, Le Chatelier's principle, in terms of the types of stresses that can be applied to the system. And I've got some videos that are going to come up and hopefully make some sense. So the first one is concentration. Right? We already looked at that one. If you add a reactant, it's going to shift to the right. If you add a product, shift to the left. If you subtract, if you remove some of the product, then the reaction is going to shift to the right. That's what Haber did when he was first developing his procedure. Right? He had nitrogen gas plus hydrogen gas in equilibrium with ammonia gas. And he was at very high pressure, very high temperature in order for the reaction to proceed. But we're going to find out in the second item here, the effect of temperature, that increasing the temperature shifted the equilibrium to the left. Right? So he got around that with two things. Well, first of all was the pressure. We're going to look at that one also. And then he used a catalyst. He used finely divided iron as a catalyst. And then when the reaction was moving along, he bled off some of the reaction mixture and cooled it. And if you cool it, the nitrogen and the hydrogen stay gases because their boiling point is very, very low, but ammonia is not. So you cool it enough for ammonia to drop out as a liquid. And then you take what's left over and put it back in the reaction vessel. And you just keep cycling it. All right. So what's the effect of concentration? We've looked at that. Now let's see a video of it.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We filled 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay, I think I got that one right. Or does it form a solid? Can't remember. Anyway, the first 2 examples were easy to follow because we added iron and then we got more of this, and we added thiocyanate, we got more of that. But the subsequent examples were using a method called coupled reactions. We coupled a reaction with this reaction in order to remove some of the reactant. The hydroxide removes some iron, The silver removes some thiocyanate. I think they use mercury too as a possibility to remove some of that. And what that did was when you remove some of these, it shifted back this way and you lost that red color. So in the lab that we're going to do next week, we're going to use coupled reactions, several of them, right? And we should have time. We can discuss it a little bit at the end of this session. Now we got the effect of temperature. So when we change the temperature, I've already said, and it's true, that we change the K. How do we shift the K? Well, the best way to understand this is what's the enthalpy of the reaction? Is it an exothermic or an endothermic reaction? In this case, the Haber process is an exothermic reaction. So the way I make this easier to follow is I put the heat on the product side if it's exothermic, right? The value is going to be negative anyway. But if I put it over here, then that helped me understand that in this equilibrium situation, this is a product. Heat is a product. So what happens if you increase the temperature? You're adding heat to this side, and that shifts back this way. And that also changes the K, because if you shift back this way, then you're reducing the size of the numerator and increasing the size of the denominator and decrease the K. That was Haber's problem. When he increased the temperature to 800 degrees Celsius, he was adding a lot of heat. He was doing it for kinetic reasons, to get these guys with enough energy to react. But he was shooting himself in the foot at the same time by adding heat and driving the reaction back this way. So he sped up the reaction to go that way. I mean, it didn't change the equilibrium, right? Catalysts don't change equilibrium. They only change the speed of the reaction. And sending everything this way faster allowed him then to bleed off and extract product and then feed the reactants back in. So he kept the cycle going that direction by feeding in and removing ammonia. Okay, so I got another. This guy has a British accent, I think. All right. So you may think that Haber should have decreased the temperature, right? And that would shift the equilibrium to the right, which is true. But also, the kinetics of the experiment, of the reaction, would tell you that it's not going to produce much of that anyway. So the position, while the equilibrium constant would increase in favor of the products, the equilibrium position would be way down in ammonia. He wouldn't get much out of it, even if it was favored. Right? So his approach was actually turned out to be the best. Now we have a situation where we're going to look at what's the effect of pressure on the reaction. And if we use this reaction, they're all gases. And only when there are reactants or products or gases will you have an effect of pressure on the equilibrium. So how do you change the pressure of this system? Well, one way is you can inject either one of the reactants or one of the products. But that kind of muddies the water because you're changing the concentration at the same time. We just want to change the pressure, not the concentrations. Well, actually, you do change the concentration if you change the volume, which changes the pressure. If we decrease the volume, that increases the pressure, but it also increases the concentration. Right? Well, let's look at the pressure. What happens is the system is looking at the number of molecules. On this side, we have 4 moles total, right? 3 plus 1. On this side, we have 2 moles. So if we increase the pressure, the system is going to respond to relieve that stress by decreasing the number of molecules. Right? So if we increase the pressure, we're going to shift to the right. And that was one of the reasons, not the only reason, but one of the reasons that Haber increased the pressure of his reaction to dozens of atmospheres. He increased the pressure massively because it would tend to force the reaction to move to the right. Now, another way that you can increase pressure is add an inert gas. Just inject argon in there, right? That will have no effect whatsoever because argon is not in the reaction. Okay. So let's listen to this same guy again. All right. That was the last slide. Okay. The presenter made the point that if the same number of molecules of gas on both sides, in this earlier equation, we had water reacting with carbon monoxide makes hydrogen gases, carbon dioxide. The balanced equation gives you 2 moles here, 2 moles here. Change in pressure won't affect that reaction. The other possibility is, say we have a heterogeneous equilibrium where we have a solid and a gas. You've got no molecules of gas on this side, you've got 3 on that side. Increasing the pressure would do what? It would drive the reaction to the left because you have 3 moles here and none over here. All right. So that's it for the equilibrium lecture. Now what you've got to do is look at the problems, and we'll take the review document next week and look at that before we go in the lab and do Le Chatelier principle.